Hello everyone, thanks for coming to this track. I'm Parshan Pakiman. I'm a third-year PhD student from Information and Decision Science Department of University of Illinois at Chicago. Today I want to talk about the SMOILE, which is a shopper marketing optimization and inverse learning engine. This is a joint work with Abhilash, Selva, who is my advisor, Ranga, and Rick. But to motivate this talk, let me start by shopper marketing. Shopper marketing involves designing marketing campaigns that benefiting both marketers and retailers, and that affects the behavior of shoppers along their path to purchase. Let me give you some example of shopper marketing. Shopper marketing, you can see social media campaign, TV ad, coupons and weekly flyers that you receive them before going to a store that are known as pre-store tactics. And there are in-store tactics like paper signage, end-cap display, in-store samples, and live demos that you see them when you go to the stores. But the question is that why brands do this? So the answer is simple. They do this to increase their sales. For example, Okay, so for example, here I have depicted the sales volume of before marketing in Walmart and Target. When brands do marketing, for example, M&M promote the M&M in these two stores, they increase their sales by some amount, and this difference is known as lift or marketing lift. Thus, brands design marketing campaigns to increase their cumulative lift across multiple retailers. Let's see why shopper marketing is an important problem. Shopper marketing is one of the fastest growing types of marketing for consumers packaged goods, and it explains 3 to 5% of total lift. So this percentage in this context is actually significant and plays an important role. If you look at this chart that I have here, from 2002 to 2010, the share of shopper marketing from total budget is increased from 3% to 8%, and around 2017, this percentage is 13%. Also, if you think of this problem as a practical perspective, this is a challenging problem to first mine the historical marketing campaigns data and lift data, and based on that knowledge, design marketing campaigns for future. Let me answer why this problem is challenging. To do that, we need to first look at how brands design marketing campaigns. Brands receive multiple sources of data that are historical data. For example, they have shopper marketing tactics historical information. They have non-shopper marketing historical information such as seasonality, it could be competitive effect information, and etc. And they have this lift information that usually external vendors provide this information. This total lift says that in a particular week, if they have some shopper marketing tactics, how much their sales increment or their lift is. So having all these sources of information and some business constraints such as budget and planning, brands needs to plan for shopper marketing tactics. This step is not a one-shot step. In fact, there are many back and forths that brands need to do and to design these marketing campaigns for a specific product in a specific retailer. After this step, they basically use the future. Use this campaign for future, and they observe realization of lift and sales. Let me zoom into this planning part. The planning is itself a sequential decision-making process over a finite planning horizon. For example, if you think of this example, that one brand wants to design a marketing campaign over 6 weeks, and the brand wants to use demo and TV ad. Maybe in Walmart, in the first 3 weeks, demo is used, and for the last 4 weeks, the TV ad is applied. This is one example why the shopper marketing design is a sequential decision-making problem. Another fact in this chart is that the shopper marketing campaigns that are used in future, as well as the realization of lift and sales, will become historical data as we go forward in time. So this shows that the planning has two aspects. First, it's a sequential decision-making process. Second, it is the data generation process in our setting. Thus, when we want to mine the data, we need to respect these two facts. Let me show you how existing and traditional models work. So, going back to the example that I previously mentioned, here we have a campaign over 6 weeks for demo and TV ad. We have historical campaigns, and for each week we have this total lift. Brands usually use marketing mix model or media mix model to attribute a portion of this lift that is attributable to demo or TV ad, and some portion of this TV ad is actually attributable to non-shopper marketing factors like weather conditions, seasonality, and so on and so forth. So these media mix or marketing mix models are very strong to capturing non-shopper marketing factors. They can handle very large array of exogenous factors like these non-shopper marketing tactics. However, they do not explicitly capture the business constraints that usually exist, and they do not explicitly capture temporal link between actions. By temporal link, I mean you may have demo in the first week, and this demo in the first week may affect the lift of the later weeks. These existing models do not explicitly capture this. So after having the lift attribution, brands use this attributed lift in an optimization problem to design a marketing campaign. Now, let me discuss how our model views to look at this problem. Our model actually have this viewpoint. We have a planning and lift attribution as a major steps in this process. As I mentioned, the lift attribution or mining the data should respect the data generation process. The data generation is in fact a sequential decision-making process. So SMOILE, our approach, thinks of this problem as a mirror images of each other. For example, so here, planning is a mirror image for the lift attribution. If you think about planning as a reinforcement learning, then attributing the lift or mining the historical data for shopper marketing is an inverse reinforcement problem. This viewpoint to designing a marketing campaign, as long as we know, is new in this context of shopper marketing campaign design. And now let me discuss about our contributions. So I think one of my slides are swapped. I should go to, sorry, this page for my contributions. Yeah. So regarding the related literature and contribution, there are empirical optimization and inverse reinforcement learning. These are very powerful for capturing the temporal link of action and modeling the problem as a sequential decision-making process. However, specific to our setting, in fact, the empirical optimization cannot be directly used because we don't have access to the attributed lift. We need to first compute the attributed lift and then use that for designing marketing campaigns. And in fact, in the inverse reinforcement learning or IRL setting, usually there isn't a lot of constraints such as business constraint, budget, or planning. Thus, we need to somehow incorporate the business constraints within the IRL context. Okay, so another trend of works in the data-driven optimization are also related to our work. In data-driven optimization, you can merge multiple sources of data in a huge optimization problem, and you can incorporate different business constraints. However, it is not necessarily capture the temporal link of actions or this sequential decision-making. So what we do, we come up with a unified approach that is a SMOILE. That is a data-driven optimization that incorporates the inverse reinforcement learning constraints, and it has these business constraints as well. And on a unique data set, we show that how it performs. And we show that when you respect how the data is generated in this process, you can improve the existing models. Okay, so let me go back to the slide that I was in. Okay, so sorry about this problem. Okay, so now I give you a big picture about these mirror images. Let me go to the details of our approach. In our approach, we need to model the lift. Our lift consists of summation of two parametric functions. The first one is due to shopper marketing effect. The second part is non-shopper marketing effect. Specific to the shopper marketing part, we want to leverage the information about consumers' behavior to design a parametric model of lift. The first model that we have has a base effect and interaction effect. The base effect checks if a tactic is active in a particular week or not. And the interaction effect basically ensures that if two tactics are simultaneously active in a particular week. Another effect that we consider is a weighting effect. In the weighting effect, if you have a promotion, consumers may wait until the very last week of that campaign to leverage the possible marketing tactics that may use in the future weeks. So this is called the weighting effect. In the second model, we have the weighting effect as well. And in the third model, we have the satiation effect. The satiation effect says that the lift is a concave function of the length or duration of a promotion. If you have a promotion of 10 weeks, then the lift is not linearly scaled with the duration of a promotion or a marketing campaign. Okay, so this is a detail of lift. We numerically show that if you leverage the information about consumers' behavior, you can get a better predictive models of lift. So here I want to briefly discuss these data-driven optimization problems. So we have the lift attribution, inverse reinforcement, inverse learning, and the tactic planning optimization. Here is the lift attribution. The objective of this problem is to compute parametric function of lift. We have two parameters, beta and theta. One is for the lift due to shopper marketing tactics. Another one is due to the non-shopper marketing factors. Here we maximize the lift across multiple retailers, across a finite planning horizon. And we have a constraint. The first set of constraints make sure that our parametric function of lift is lower bound on the historical lift data. The second ones are actually the IRL constraints, or inverse reinforcement learning constraint. You can think of this constraint as follows. This mu parameter that I have here ensures that we assign a lift to the existing historical marketing campaigns that is not worse than any other possible marketing campaign that could be used in the past by factor of mu. You can think of it in this way. If you have a marketing campaign from historical observation, then that campaign is mu away from an optimal campaign that could be used in the past. So it's interesting to see how this mu works in the numerical study. As mu is getting large and large, it means that the historical data is not very reliable. They are basically not close to an optimal campaign. After having the attributed lift, we plug in the output of this math program into this tactic planning optimization to compute a tactic or the marketing campaign that can be used in practice. Okay? So let me go to the numerical study part. We have data from different product categories that are frozen, breakfast, and wings. We focus on two major retailers in the US. We have data of 60 to 64 weeks for each retailer. We consider 11 and 9 different shopper marketing tactics. And all the models are implemented in Python, and they solve with Groovy optimization solver. So as I mentioned, in the non-shopper marketing factor, we didn't have enough information in the historical data to approximate that part. We approximated that part via a time-varying constant. The business of this paper is actually attribute the shopper marketing part properly. I'll show you that how we attribute the lift due to shopper marketing in few slides. Okay, let me talk about this performance on the train set. On the x-axis, you see this mu, which when mu is very small, it means that the inverse reinforcement learning constraints are not tight. Are tight. And when the mu is large, we basically relax the inverse reinforcement learning constraints. And in the y-axis, we have mean average training lift. And the red line that you see on the top is the existing historical lift. This plot shows that when inverse reinforcement learning constraints are active, then the model that is learned is different when these constraints are inactive. These models these golden points that I have here, these are when the inverse reinforcement learning constraints are not active. Okay, so now we can look at the performance of our model on the validation set. On the validation set, the golden points are showing the existing traditional models when the IRL constraints are not active. And you can see that at the optimal when we cross-validate the parameters of our approach, we can obtain less maximum absolute deviation in the validation set, which shows that IRL constraints not only change the model, but also they improve the performance of model on the validation set. Okay, with this, we can go to the performance of SMOILE on the test set. Here I have 3 models, as I mentioned before. So in the first model, you can see that, in the very top, in the red line, I have the historical test set lift value. And you can see that the first model seems pretty good fitted this on the test set. But this is tricky. In fact, as I mentioned, we approximate the lift due to non-shopper marketing factors with constant. If constant plus shopper marketing can explain all the lift, then something is weird. This doesn't make sense. We think of this as a spurious result. However, when we incorporate the consumer's behavior in Model 2 and Model 3, we see that there is a gap that we can't explain, which makes sense. And you can see that the shopper marketing in Model 2 explains 0.5% of the total lift, which is very small. And as we include the satiation effect in the Model 3, we increase the shopper marketing to around 3%, which matches with the practice. Okay, so this shows that incorporating consumers' behavior and adding the inverse reinforcement learning constraints into mining the lift, in fact, improves the model. Okay, let me just conclude my talk by few points. SMOILE is an integrated framework that basically combines multiple sources of data and uses data-driven optimization to solve this problem. It in fact makes the lift attribution and tactic planning consistent by looking at these two problems as mirror images of each other. We incorporate the consumer's behavior in our problem, and we show that it is important to incorporate them. It streamlines the implementation by looking at this problem as a tractable optimization problem. And it can be efficiently solved via commercial optimization solvers. Thanks for listening to this talk. If you have any comments, please send me an email in this email address. Thank you.